Today we shall start. So far we have been looking at three fields, quantization of three fields, and we have also looked at how to construct actions from the gauge, from the principle of gauge invariance, from the gauge principle. In order to describe interactions, I have mentioned that we should know how particles move in space-time, and for that uh, we have we have looked at the propagator or the Green's function of the real scalar field, and we have also shown in the last discussion that the propagator of the Green's function is basically equal to the vacuum expectation value of the time-ordered product of two real scalar field operators. So that was a very crucial result that we derived in the last discussion. Now we are in a position. So you may ask that we have derived the propagator of the real scalar field. So what about the propagator of fermionic fields and gauge field propagator for electromagnetic field propagator? What about those fields? So we shall derive the propagators of those fields in some later discussions. For the time being, for today, what we shall do, we shall look into the formalism which would help us to describe interactions among quantum fields. So let us start with that formalism. And that formalism is, you must have learned already in your quantum mechanics course, is the Dirac interaction picture formalism. And we shall look into it in great details. Because this is the formalism that is needed in order to deal with quantum field theories, in interacting quantum field theories, self-interacting quantum field theories, as well as fields, two different species or two different fields which are interacting among themselves. For example, quantum electrodynamics. So this formalism will help us to deal with interacting theories. So to start with, what we shall do is we shall look into the Heisenberg representation. You must have seen what this is. Heisenberg representation. So in this representation, as I have mentioned in your path integral, and you have also seen in your quantum mechanics course earlier, that in this representation, the operators, which I denote as O hat, these are time dependent, and the state gates, so these are the state gates. So these are time independent. Okay. This is the Heisenberg representation, but as I mentioned in your path integral course, when I taught you path integrals in quantum mechanics, the operators are time dependent, state gates are time independent, but the base gates with which you will take the representation to write down wave functions, the base gates are time dependent. So here, in this case, the Heisenberg representation, if H hat is the full Hamiltonian of your theory, then and let us assume that H hat is time independent. It is a time independent Hamiltonian. Then in this representation, you know that you can write this down as H hat T, O hat, and I should write O hat 0, which tells you that this is a time t is equal to 0, but let us omit this notation. Whenever I write this in this way, it means that the operator is defined at time t is equal to 0, and then I have e to the power of minus I of h bar and Newtonian. And from here, you know that so in this representation, if I take the dt of this, h hat is time independent. So you just compute this thing, then you will get I by h bar and Newtonian e to the power of one term plus 1 by h bar and to me and t 4 hand. We have minus I by h bar this. Okay, and this is equal to therefore I by h bar. I have missed some term, I think. There will be a h bar here. And now from here you can see that this term commutes with this term commutes with this term. So you can immediately write this as e to the power of. So what you can do is this is h hat, and this term by definition is O hat p, and this is again O hat p, this is h hat, this thing, and then therefore this thing is equal to nothing but, I'm writing it over here. I hope you can see this. Therefore this thing I can write it down as commutator of h hat with O hat p. Therefore what we have now is IH bar equal hat. Should remember that this holds when H is considered to be time independent. And this is the standard Heisenberg equation of motion that follows. So this follows from this. This is the operator which is time defined at time t is equal to 0. So in the Schrodinger, so this is basically the operator in the Schrodinger representation. In Schrodinger representation, you know that operators are time independent and state gates are time dependent. So now let us see how should the state gates in the Schrodinger representation be, how are they related to state gates in the Heisenberg representation, and that all of us know because you have this thing, you have the Schrodinger equation. This is the state gate in the Schrodinger representation. This is time dependent, and that is equal to h hat. This is the time dependent Schrodinger equation. H hat is time independent, and from here you can immediately write that psi t is or you can write this as 0, which is nothing but, this thing is nothing but state gate in the Heisenberg representation. The state gate at time t is equal to 0, and state gates, therefore they are time independent, and time independent state gates are basically in the Heisenberg representation. Therefore you can at once see that state gates in the Schrodinger representation is related to state gates in the Heisenberg representation in this way. And this is then this actually follows from the time dependent Schrodinger equation. Now you know that the results that you get after computation should be independent of the representation in which you are working. So all the matrix elements that you calculate, that these should be independent of the representation, and you should check it. So for example, if I calculate the matrix element of this operator, so this operator is time dependent, therefore it is in the Heisenberg representation, and it is I'm calculating sandwiching it between two state gates which are time independent. So these are all these things in the Heisenberg representation. So this must be equal. This must be equal to psi t in the Schrodinger representation. I'm just omitting s for the time being, because just remember that this is time dependent, therefore this is in the Schrodinger representation, and that this must be equal to this. Right? Matrix elements should be the same. And from here also, if we just plug in this the form of O hat t, which is e to the power of I by h, bar this O hat e to the power of minus I by h bar h hat. You just put it over here. From here, you immediately see that ket psi t gets identified with this thing e to the power of minus this thing psi 0. So even from the equality of matrix elements in different representation, this relation follows. So everything is consistent. So let me just recall once more, summarize. In Heisenberg representation, state gates are time dependent, independent, operators are time dependent. You get the Heisenberg equation of motion, which governs the dynamics of the system. In the Schrodinger representation, state gates are time dependent, operators are time independent, and the dynamical evolution is governed by the time dependent Schrodinger equation. Now there is another representation, which is the Dirac representation or interaction representation. And you will realize later, Dirac representation or interaction representation, you will realize later that why this representation is very, very important when you deal with interactions, interacting quantum fields. This representation is very important. Because it would be very difficult to write any equation in the Heisenberg representation or the Schrodinger representation. It would be very, very difficult to write anything. Schrodinger representation you can still write down, or you can write down quantum field theories in the Schrodinger representation, but it would be very difficult to write equations in the Heisenberg representation, and it is there that the Dirac representation comes to be very handy. In the Dirac representation, it is basically a mixture of both the Heisenberg and the Schrodinger representation, in the sense that in the Dirac or interaction representation, both the state gates and the operators are time dependent. So, how are operators? So let me write an I over here, which represents I at the interaction representation. Operators are time both operators and state gates are time dependent. This operator is related to the Schrodinger operator in the following way. So what we do is we just partition the total Hamiltonian, the full Hamiltonian, into h hat naught plus b hat. This h hat naught is the free part. Is the free part of the full Hamiltonian. That free part, by free part I mean the part that has no interaction, the part that we have been dealing so far. All the free Hamiltonian of the real scalar field, complex scalar field, Dirac field, electromagnetic field. So these are all free fields, and the Hamiltonian for that fields, for those fields are represented by this term h hat naught, and v hat represents the interactions. So here, take it, you define this thing in this form. And from here, you can immediately see that the dynamical evolution of this operator in the interaction representation is basically governed by this equation. Just as in the case of the Heisenberg equation of motion, dynamical evolution is governed by the free part, not the full Hamiltonian, by only the free part of the Hamiltonian. That is how the dynamical evolution is governed. What about the state gates? See, the state gates, you should remember the following principle, that whatever representation you work with, the matrix elements in each of the representations, whether Dirac or Heisenberg or Schrodinger, all the matrix elements in each of the representations should be equal. From there, using that principle, you can actually find out how should the state gate in the interaction representation be related to the state gates in the Heisenberg representation or the Schrodinger representation. So you can actually find it out. Let us find it out and see what happens. So the equation that we should have is the following. you should have O hat T. This is I in the interaction picture. I'm writing wrong. Sorry, this is in the interaction representation, the state gate. This is the state, this is the bracket in the interaction representation, and the matrix element of the operator. This is also in the interaction representation. So let me write this I here. O hat I. This must be equal to psi t s, this bracket, that is the state gate in the Schrodinger representation. This operator in the Schrodinger representation, this is time independent. So this is what we should have. Now let us just plug in what O hat I here is. So if you do that, you get IT I e to the power of I by h bar h naught t O hat that is equal to, this is equal to this. Okay, this is equal to this. This thing is equal to this, and this thing is equal to this. And therefore, from here, it immediately follows that e to the power of minus I h bar h naught t psi I must be equal to s, right? And therefore, from here it follows, this implies that psi t I, the state gate in the interaction representation, which is also time dependent, is equal to e to the power of this times the state gate in the acting on the state gate in the Schrodinger representation. So this is the relation, and this follows from the equality of the matrix elements. So once you define how the interaction picture operator is related to the Schrodinger picture operator in this way, everything follows. And therefore, the state gate in the interaction representation, how is it related to the state gate in the Heisenberg representation? You just need to apply the result, how this and Heisenberg representation gate are related, and that is straightforward. It is I by h bar h hat naught t e to the power of minus I by h bar h hat t psi. This I don't write t is 0. I don't write any t, therefore that is in time independent, and that is in the Heisenberg representation. And therefore the interaction picture K is related to the Heisenberg picture K in this fashion. And in general, let me just mention, I forgot to mention here, see the full Hamiltonian, this all these things that I've been doing here, these are basically time independent. This is, I consider this to be time independent. So at time, everything is at time t is equal to 0. Therefore, these operators are basically at time t is equal to 0 means they're time independent, and therefore they're in the Schrodinger representation to start with. This is the free part of the Hamiltonian, and this is the interaction part of the Hamiltonian. Everything, since this is time independent, this is also time independent, this is also time independent. Everything is time independent. Only one thing that you should remember, that in general, h hat naught do not commute with v hat. The interactions and the free part of the Hamiltonian do not commute with each other, and therefore, since this is true, therefore h hat also does not commute with the interaction part. So you should just remember this. H hat naught does not commute with this, and therefore you might be tempted to write this in the following way, that this is e to the power of I by h bar h naught. So you may be tempted to write this as e to the power of I by h bar h hat naught minus h hat into t, and so on. And then you may write this as minus v. But this step is not correct, because if you do this, since the operators do not commute, you should apply the Baker-Campbell-Hausdorff formula. But this is not the Baker-Campbell-Hausdorff formula. There will be a commutated term, and therefore this is just not this thing. So this step is not correct. Is it okay?
Yes, sir.
Okay. This part of this thing is not working. Okay. So what we have done is we have related how the state-gate interaction in the interaction picture is related to the Heisenberg picture. Now the question comes is how, see, the equation of motion, in case of the Heisenberg representation, there was only one equation of motion, the time evolution dynamical equation, because only operators were time dependent, and therefore state gates are time independent, so they will not evolve, so there is no equation for the state gates. And similarly, that was true for Schrodinger representation. Operators were time independent, so there is no dynamical evolution equation for operators. There is only dynamical evolution for the state gates, and this is the Schrodinger time-dependent equation. In the Dirac representation, both the state gates and the operators are time-dependent, and therefore there will be two dynamical equations of motion. Both of them will evolve with respect to time. The operators, as we have seen, these operators evolve with respect to h naught. Okay, the h naught is responsible for the dynamical evolution of the operator in the interaction picture. Now, the question is, who is responsible for the dynamical evolution of this state gate in the interaction picture? So, it is straightforward to do this. What we need to do is, we just need to take a derivative of this equation. Let us take a derivative of this equation. If we take a derivative, operate it with a time derivative operator, then what we shall have is we get IH bar, we get H hat naught, and e to the power of I by H bar, H hat naught sin T, psi S. So this is the first term, and the second term will be e to the power of I by H bar, H hat naught sin T, del T. You can also do the calculation by taking into account this relation. This is equal to I by H bar I can write Z. I can write this and this commutes, because this is also H naught, this is also H naught. Therefore, I can write e to the power of I by H bar H hat naught. This, and here I apply the Schrodinger equation, time-dependent equation. And if you apply the Schrodinger time-dependent equation, what we shall get is IH bar this thing. So this will be minus I minus I by H bar. This, and del T psi T S. So that will give us H hat. So what we have done is we have applied the time-dependent Schrodinger equation. Let us write it down here. So now we can combine this term with this term. can write this as I by h bar, e to the power of I by h bar, but not t. This is h hat not minus h hat I t. Yes, but this thing is nothing but minus d hat. This is equal to minus I by h bar e to the power of I by h bar h hat not d hat times its. Now what we shall do, insert an identity operator here at this point. And what will be that identity operator? That identity operator will be e to the power of minus I by h bar h hat not t. Therefore, I have to just write another thing like this. Then we have its. Okay. From here, we shall immediately get equal to. See this part is again by definition it is minus I by h bar. This is interaction. The interaction part of piece of the Hamiltonian we have in the interaction picture because you have these operators here. Therefore, this is v hat it now becomes time dependent. So this is the interaction in the interaction part of the Hamiltonian in the interaction picture. And then we have this thing. But what is that? That we have already seen that this piece is nothing but the state gate in the interaction picture. Therefore, this is psi t I, and therefore now we have the equation of motion. This implies that I h bar del t psi t I is equal to v hat I t. So this is the equation of motion, or this is how the state gate, the interaction picture evolves with respect to time. And the evolution is actually governed by the interacting part of the full Hamiltonian in the interaction picture. In the interaction picture, it is governed by v hat, but v hat then you have this e to the power of I by h bar h naught operators acting from both sides. And therefore, that gives you the operator in the interaction picture. So the time evolution is governed by like in this way. This is the time evolution equation in the interaction picture. Is this okay?
Yes, sir.
Do you have any questions? You should ask questions. Are you sleeping?
No, sir.
No,
No,
that
sir.
I understand you are not sleeping, but others?
No, sir.
No, I think
It's okay.
it's okay.
No, sir, it's not okay. I have a question. I have a doubt, but not a proper question.
Please ask your doubt.
Sir, we have taken here the Schrodinger's equation as correct and the time evolution of Heisenberg representation as correct. But I mean, we have applied these things, but we have advanced from that, and we have already used the relativistic part, advanced quantum mechanics. So, how can we take those equations as correct?
Which equation? Just repeat once more.
Here we have used Schrodinger's equation,
Okay.
and previously we have used the time evolution of the operator in Heisenberg representation.
Right.
But now we are doing a thing for more general, I mean, a relativistic case. So how can we take those equations as correct or the time evolution is
I
taken?
understand your question. Is this Joyarshi?
Yes, sir.
Okay, this is a very important question, and rather this is a very important confusion that you have in your mind. What you are saying is that we are doing relativistic quantum field theory. If I have understood your question correctly, what you are saying is that we are doing relativistic quantum field theory, but we are applying Schrodinger equation here. Why are we not applying relativistic equations? Right? This is what
Yes,
you are
sir.
asking?
Yes, sir.
See, the answer to this question is very simple, but this actually is a very important concept, or you should clear this doubt in your mind forever, for once and forever. See, what we are doing is, see, this is also a Schrodinger like equation, right? Or in the state
Yes,
in
sir.
the this is the standard Schrodinger equation, right? In the Schrodinger representation, the time dependent Schrodinger equation, as we say,
Hmm.
right? But this time dependent Schrodinger equation has nothing to do with non-relativistic theories or relativistic theories. This is generally true for any theory. There is no relativity or non-relativistic. There is nothing non-relativistic or relativistic about this equation. First of all, we should get this thing clear from your minds. Only when you put h hat, this Hamiltonian, to be equal to minus h bar square by 2m grad square plus potential, that is the non-relativistic form of the Hamiltonian. So putting h hat is equal to p square by 2m plus v hat, which is equal to minus h bar square by 2m grad square Laplacian plus the potential. So that operator is a non-relativistic operator. So then only you are doing non-relativistic quantum mechanics. But when you put h hat to be in the Dirac form, like as we took,
Alpha.
what did
Al alpha
right?
dot p minus c.
Correct, correct. Plus beta mc square. When you put Hamiltonian in the relativistic form, then this will give you the relativistic equation, quantum mechanical equation.
Okay.
This has nothing to, this is Schrodinger equation, correct?
Hmm.
But this has nothing to do, this is a very general thing. When you choose the Hamiltonian to be in the non-relativistic form, then it is you are doing non-relativistic quantum mechanics. When you choose Hamiltonian in the relativistic form, you are doing relativistic quantum mechanics.
Okay, sir.
Okay, this is
Hmm.
not, equation is not non-relativistic. This is the confusion that you are having in your mind. This equation is complete, takes into account everything.
Yes, sir.
It's an important question. This doubt should get removed from your mind.
Yes, sir.
Okay, you should ask many questions. Ask as much questions as you like, because we have already proceed. We have made a lot of progress. Think about more doubts or more problems that you may have in your minds.
Sir, I have one doubt, but it is not from here actually. In field theory, actually.
In field
Uh,
theory, you have a doubt.
yeah.
What is that doubt?
Sir, when you are doing the discrete case, I mean, not considering the continuous case, is it actually satisfying causality? I mean, because the spectrum is becoming discrete when you are considering the discrete case.
Discrete case means what?
The mode expansion when we are considering Kronecker delta instead of Dirac delta.
Yes, there is no problem with causality. Everything is causal here. Why should you? Because see, in the discrete case, what we are saying is that we are putting the fields in a box, and we are imposing periodic boundary conditions at the walls of the box. If it is one-dimensional, then we are putting periodic boundary conditions at the two ends. If it is two-dimensional, there are two directions in which you have to put periodic boundary conditions, and similarly for three dimensions, and similarly for any general d dimensions. And when you impose periodic boundary conditions, then the eigenfunctions, which are the solutions of the classical field equations, those eigenfunctions has that k thing, the momentum. The momentum gets discretized, and that has nothing to do with quantum mechanics or causality. That takes discrete values because the simple reason for that is the following, that you have imposed periodic boundary conditions at the ends of the box, and the fact that you are doing things in a consistent way is clear from this, that if you take the box, if you take the length L to infinity, in that limit k will take a continuum of values, and then the summations will get replaced by integrals, and Kronecker deltas will get replaced by Dirac delta functions, and so on.
Okay.
Okay. So let us do one more thing and then end today. So if you remember correctly, that the state gate in the interaction representation is basically e to the power of I by h bar, h hat naught, e to the power of h hat t. So this is in the Heisenberg representation. This psi is time independent. This psi is time independent. So what I will do is I will define an operator, a new operator, which is basically this. And what is this operator? This operator is, you have t e to the power of this thing. This operator I define it as u hat t. And what I want to find is the following. It's very simple. I want to find an evolution equation for this operator. It is simple to check that this operator is actually unitary operator. That is, u hat dagger u hat p is equal to identity is equal to u hat p u hat dagger. Then just check it from the definition of this operator. Take a dagger, and you will see that this holds. Is immediate. And not only that, this operator u hat p satisfies, if I put t is equal to 0, then u hat at 0 is identity. This is unitary operator, and this is at time t is equal to 0, this operator is an identity operator. And that is what it should be, because at time t is equal to 0, see, all the representations, all the state gates, or all the operators in different representations match at time t is equal to 0. Right? So that is what we get. So this is the initial condition. And now what I want to do is to find a dynamical evolution equation for this operator only. And let us see how we can do it. So if I take, we know that IH bar IPI, that is equal to, therefore, IH bar del T u hat T this. So this del T operator will act only on this operator because this is time independent. But what is this equal to? According to this equation, this is equal to V hat I T, that is the interaction in the interaction picture operator, and psi Ti is nothing but u hat T IH. This by definition is psi T u hat T psi H. And therefore, the equation of motion for u hat is the following: IH bar del T u hat T is equal to v hat I T u hat. So this is the dynamical evolution equation for this operator u hat t. I think this is a nice place to stop here today. We shall continue from here on Monday. So what we have done today is find out. We have found out dynamical evolution equations for psi ti for state states in the interaction picture. Dynamical evolution, and that is governed by the interaction part of the Hamiltonian in the interaction picture. The dynamical evolution equation for the operators in the interaction picture are governed by the free part of the Hamiltonian h hat naught, and the dynamical evolution equation of this operator that I have just now defined, u hat t, is governed by, once again, the interaction part of the Hamiltonian in the interaction picture. And as I mentioned, that this equation is a very general equation, time-dependent Schrodinger equation. This does not mean that this equation holds only in the non-relativistic regime. No. If you remember correctly, it was from this equation that you derived, that you obtained the Dirac equation. The time-dependent Dirac equation is basically nothing but I bar del t is the Dirac wave function that is equal to the Dirac Hamiltonian acting on the Dirac wave function. Okay. So, do you have questions? Yes or no? I find there are seven people. So, 3 of you or 5 of you are missing today. Maybe. Okay. So let us stop here. Thank you very much for today. We shall continue on Monday at 10:45.
Okay, sir. Thank you, sir.